Today is day 8. The in-class version of this class have had some snow to deal with the last couple days, but those of you that are watching on TV, it just looks like we're just flowing right along. We in here last time talked about exponential functions, and we didn't quite finish, but we did get to a point which I think is a good breaking point. We started getting ready for talk about the number e, the base of the natural exponential function. I don't know if you've referred to it as the natural exponential function, but I bet you that you've referred to the natural logarithmic function. So those two are certainly related. And that's where we're headed also. In addition to looking at exponentials, we're going to turn those things around, or hopefully have the ability to turn them around and look at their inverses. And I think we'll be able to get to a little bit of section 1.6 today, which deals with inverses. But let's finish up exponential functions. We looked at some base 2 functions. We also looked at a base 1/2 function. Actually, those could both be considered to be base 2 functions. 2 to the x, and the other one, 1/2 to the x, is the same thing as 2 to the negative x. So in a sense, kind of 2 to the x and 2 to the negative x, both base 2 functions. We did look at an example. We did not battle the function itself all the way to the equation. In the first example, the population growth problem, but it is used a lot to model growth functions as well as decay functions. I think we did do battle with the decay function, and it was a half-life problem. And we had some data points, and we kind of started building our own function with base 1/2, and we're able to build our function that we think matched the data that was given to us in the problem. So you've seen a couple of different ways that those can be used. Let's continue today with this number e, which is the base of the natural exponential function. I'm going to need some calculator help here, so if you have a calculator handy, if you can feed me some numbers, I would appreciate it. I think we talked about the other day a good approximation for the number e is 2.718, and I'm sure that you have used many times the number pi, and probably have it committed to memory to the point where you can't ever forget it. The decimal approximation for pi is what? 3.14. Could you give me 7 or 8 more decimal places? Maybe somebody could. 3.1415926. You could probably give me more. But most of you know pi, 3.14. This is a similar type of number. And I think it would probably be to your advantage to memorize, if you haven't already, that e is approximately 2.718. Now let's keep that in mind. That's not exact, and we're not going to be able to write down an exact decimal equivalent because of the nature of the number, the type number it is. But let's look at one of the ways we could come up with this number e, and we're certainly not going to be able to evaluate the limit here all the way out to infinity, but let's get an idea that it does in fact generate the number e, 1 plus 1 over x to the x, as x is allowed to approach infinitely large values. Let's just start with, I know this isn't very close to infinity, but let's kind of see what happens with this. Let's start with x being 10. Keeping in mind that we want x to get larger and larger and larger. So if x is 10, we've got 1 plus 1 over 10 to the 10th. Now I know that you're pretty savvy mathematicians. I know that you've done a lot of limits, and that you've evaluated, for example, what happens to 1 over x as x approaches infinity. So if you look at this in pieces, and unfortunately this doesn't work in this problem, but if you look at this in pieces, what happens to 1 over x as x gets large? That approaches 0, gets smaller and smaller, right, as x gets larger? 1 over 600 trillion is not a very large number. So it seems like this thing inside approaches 1, right? And this would be very close to 1 raised to higher and higher powers. So intuitively you might say, oh, that's not E, that's 1, because that's practically 1 being raised to some tremendously large power. But because it's a little more than 1, and because the power is extremely large, it's a whole lot different from 1 in final answer. So if x is 10, somebody run that through your machine. What is 1 plus 1/10 raised to the 10th?
2.59.
2.59 approximately? Okay, that's getting pretty close to the value of E already, and we're not very close to infinity for the value of x. So you can see that inside portion getting closer and closer to 1, but because it's being raised to such a high power, it's very, very different from 1. What's 1 plus 1 over 100 raised to the 100th power? 7.
705.
705. Again, we're not very close to infinity, but we're pretty darn close to the value of E. So let's let x get pretty large here, 100,000, still not really close to infinity, but pretty large. What's 1 plus 1 over 100,000 raised to the 100,000th power? Anybody run that through your machine?
0.7182.
Now, is that the value of E? No, it's not. Now, to the 3 or 4 decimal places that we're looking at it right now, it might be what we're going to use for an approximation for E, but that's not quite E yet. The only way it's equal to E is to let x go all the way to infinity. But this is one way of generating the number E. Now that might still seem like kind of a strange number to you, and truthfully I think it's kind of strange too, but it is amazing in mathematics how many times that number comes to the surface and how useful that number becomes. In fact, one of the many rationale that I've heard for using this number, one of the newest ones, I found by reading this book, this version of this book. And your authors talk about this number E, that if you look at y equals 2 to the x, and y equals e to the x, and y equals 3 to the x, well, clearly, y equals 3 to the x, y equals 2 to the x and y equals 3 to the x, they sandwich y equals e to the x because the number e is somewhere between 2 and 3. So if we drew a picture of this, you would see e to the x kind of always sandwiched in between these two functions. And the other two are a lot easier to deal with, especially as far as plotting a few easy points. But if you'll analyze what's going on at the point 0, 1, which is on all three of these, everybody agree with that? If you put in x equals 0, you get y equals 1 on all three of these. On the first one, the slope of the tangent, better not use that notation, the slope of the tangent So if I were to draw that graph and the slope, this is just an error on my part. I was going to use a different notation, but then I realized we haven't covered that yet, so I better not use that notation. Slope of the tangent on this function at that point is 0.7. The slope of the tangent on y equals 3 to the x at this point is 1.1. Well, very conveniently, the slope of the tangent of this one that's sandwiched in between these two at this point is the nice, clean value 1. So that's a feature that, in fact, is true, that has always been true, but I've never thought of that as an advantage of using this function. But a sketch of it. Zero, 1 is that point we're talking about. When x is 1, that's the value e raised to the first, which is e itself. 2.7. Need some calculator help here. When x is negative 1, what's e? Use your machine to help you with this. What's e to the negative first? Somebody run that through your machine. What's 1 over e?
0.368.
0.368, so a little bit more than a third. So we get this graph that has this shape, which doesn't surprise us. That's what exponential graphs look like when the base is larger than 1. And what I just said is that the slope of the tangent line, so if I come in here at the point 0, 1 and draw a line that's tangent to this curve, that line has slope 1, which is a nice convenient feature of the function y equals e to the x. So if you go up 1 and over 1, from that point you would actually be drawing a line that is in fact tangent to the curve. And I think I've mentioned the fact that slopes of tangent lines will be a critical topic in this course. Again, we're in that kind of review mode now, but it won't be long where we'll be talking about kind of average rates of change, which would be the slope of a curve. Curves have slope too. Slope of a curve between 2 points on that curve. And then later we'll be looking at the slope of a curve at a specific point on that curve. So that would be a tangent to the curve, and that's kind of where we're headed in this course. So y equals e to the x, and when we get to derivatives, you'll see it's one of the easier derivatives of all of them that we examine. So it just has some nice features, y equals e to the x. So this natural exponential function, as odd as it might seem, this base, is very convenient in mathematics, certainly in calculus. There's a nice example in your book at the end of section 1.5 on e to the x. I've chosen another one that you may or may not have seen, but I think at some point in time you need to see this example, and it is related. So let's take a look at a function that has to do with y equals e to the x, but is not just y equals e to the x. In fact, I want us to look at two of them. Let's look at y equals e to the x one half e to the x and 1/2 e to the negative x. So a little different versions of just a simple e to the x. And then eventually I want to put these together with addition and put them together with subtraction. Does that ring a bell for anybody? If I were to write down this function, this is kind of where we're headed. Have any of you dealt with that function before? Anybody in here? Okay, well that's good. That's why I chose this as an example, because I think it's something we need to acquaint ourselves with. And if you haven't seen it to this point in time, today's a good day to look at it for the first time. All right, well let's look at this one. 1/2 e to the x. What do you think that 1/2 does to our new friend? I guess we can call it our new friend, y equals e to the x.
Stretch.
Okay, kind of stretches it in this direction. Or if you want to think of it, slowing it down in this direction, right? We're taking half of every y value. So if this is, and I'll redo these, but if this is if that's e to the x, can I just go through kind of point by point and now the y values are half what they were. So at each x value, so I can come over here at this x value and say, well, I don't want this much, I want half of that. Or at this x value, I don't want all that, I want half of that, right? Or at this x value, I don't want all that, I want half of that. So if we start connecting those dots, it's a similar shape, right? Just kind of goes up a little slower because we've just basically cut the y values in half for each individual x value. So very similar there to y equals e to the x. Let's look at, I guess we ought to look at this one first. E to the negative x, and then we'll take half of those values. How is e to the negative x related to e to the x?
Flipping the y-axis.
Okay, right? We're going to just take the symmetric image on the other side of the y-axis, right? So basically, it's a role reversal, a sign reversal of the x value. So what were, when we graphed this the first time, y equals e to the x, what were positive x values, we're now going to negate them, and they become negative. What were negative x values are now being negated, and those become positive. So it's a role reversal of the positive and negative. So we should have a graph that looks something like this. So a decreasing or a decay type function. And let's stay with this color. What should those look like? Well, basically at every y value, we're going to come through and take half. So at every individual x value, look at the y value, cut it in half. So we don't want all that. We want half of it. We want half of this, and so on. So we end up with a function. That looks like that. Somewhat like the original decay function, only you want to think of it kind of taking a little bit longer for it to decay. The y values are less at each individual x value. So we have two functions, and I want to look at those simultaneously here. We have y equals 1/2 e to the x and y equals 1/2 e to the negative x. I'm going to sketch them again, but I'm going to sketch them on the same axis system. So one of them looks something like that. That was, what, 1/2 e to the x, right? Mm-hmm. And the other one looks something like that. This point right here is 1/2 for both of them. I don't know if you've ever used this graphing technique before, but if you want to come up with the graph of something that is, in this case, 1/2 e to the x plus 1/2 e to the negative x, that's kind of where we're headed, you can just add them up on the graph. At any x value, just add up the two y values. So this used to be called addition of ordinates, because that's what you're doing. For any x value, you're adding the y values. So at x equals 0, they're both at 1/2. What's 1/2 plus 1/2? 1. Just pick any point you want to pick here. Let's just say right over here. Well, I've got this much y added to this much y, right? So I'm adding the two y values at that x value. So that brings it that much above the other y value. Come over here, and I'm adding this much y to this much y, which brings it in here. And you can add as many points as you so choose here. You're going to end up with kind of a parabolic looking graph that looks like this. So the graph in green is this guy right here, 1/2 e to the x plus 1/2 e to the negative x. How many of you have a key on your calculator that's got a sign with a little h after it, or a cosine with a little h after it? Do you have that? Or have you dealt with that function before? You dealt with these before. Hyperbolic cosine or hyperbolic sine? Anybody? That's kind of what we're generating today. We just generated a hyperbolic cosine. By definition, hyperbolic cosine is that right there, 1/2 e to the x plus 1/2 e to the negative x. So is it really a cosine? No, it's not. It's not a trigonometric function. We'll have more time later to spend on these two functions, but I wanted to kind of give a first presentation today of them, because I'm reading that none of you have ever seen these before. And I think these are valuable functions to look at. The other one we're going to look at is 1/2 e to the x minus 1/2 e to the minus x. And we can graph 1/2 e to the x and then graph negative 1/2 e to the negative x and add those up. So let's do that. This one we've done already twice. Aren't you glad I chose this example? Some of you don't appear real glad today. Sorry. So we want to graph y equals 1/2 e to the x again, and this time we want to graph the negative of 1/2 e to the negative x. Now we already graphed 1/2 e to the negative x, and that looks something like this, right? What's this guy look like? The reflection on the other side of the x-axis, right? So all the y values that were positive are now negative, something like that. So we want to take its symmetric image on the other side of the x-axis. Then we'll take this graph and graph it on the same axis system with this one, and we'll again add them up. One of them's negative, but I didn't want to subtract on the graph. I wanted to add on the graph. So here are the two component pieces. There's 1/2, positive 1/2 e to the x. And then we want this one down here. And we want to add them up graphically. This is that one. Okay, the most obvious point is that x equals 0. This is positive 1/2. This is negative 1/2. What is their sum? 0. And I'm just going to pick a point. Here, at this x value, we've got this much positive and this much negative. So don't the positives outweigh the negatives there? So we want to come down from that positive just a little bit. And another point out here, there's the first one, there's the second one, which is negative, which means I've got to come down from that positive just a tad. I'm adding up the y values. So there's what the sum of those two graphs looks like. Over here, looks like the negatives outweigh the positives. So we'll come a little bit above that negative. Here the negatives outweigh the positives, so we'll come just a little bit above that. So the graph in green here is that one. E to the positive, thank you. E to the x, 1/2 e to the x, minus 1/2 e to the negative x. So you get that first one that kind of looks like a parabola, although it's not really a parabola. And this one that we call it a hyperbolic sine, but it certainly is not a sine function. But those are two functions that we'll encounter later on in this course, and when we take derivatives, we'll take the derivative of a hyperbolic sine and the derivative of a hyperbolic cosine, and they have some nice convenient properties as well. So if you've ever seen a calculator with that little sine key with an H on it, this is what it is. It's really not a sine graph. It's an exponential function. It's a base E function. Okay, why are we headed in this direction? Or what is one of the goals of looking at functions of this type? Well, we don't always have the luxury of like plugging a time into a population problem, doing what we're supposed to do to it, and it spits out the population at a certain point in time. Or plugging the time into this decay function, 2 hours later, how much of this stuff is left? Well, that's nice if all you're going to do is plug and chug with times and then how much of the stuff is left. But a lot of times, we want to know the time that elapses in order for 75% of this stuff to be decayed. Or we want to know how long. I mean, we've got this town here, and we know that due to infrastructure and water and sewer situations, we can only support 150,000 people. If the population is growing at such and such a rate, how long, if it grows at that rate, before the population reaches 150,000? How long before we outgrow our infrastructure? So sometimes it's not an exponential function that we want. Sometimes we want to flip the roles of t and f of t, or x and y, and come up with where am I headed? An inverse function, right? So maybe exponentials won't solve it, but their counterpart, their inverses, logarithmic functions, will solve those kinds of equations. So it's nice to work with functions, and in fact it's nice to work with special types of functions so that when we take their inverses, they are also functions. Here's a way, and now we're headed, if you're keeping track here, we're headed into section 6 with inverse functions and logarithms. A lot of times the original function will do the trick, but sometimes we would just like to be able to basically do some role reversal of x and y. And we want to talk about some things that are functions, and when we flip them around, they're also functions. Here are some functions in picture form, kind of a mapping type of approach. This picture is also in your text, but I wanted to refer to it, so I had it copied. So here's an example, the top one, of some pairing or mapping that we're going to call f. And it appears here that the f of 4 is 10. Does that look right to you? Mm-hmm. The f of 3 is 7. The f of 2 is 4, and the f of 1 is 2, right? And that's all we know about, is those 4 points or those 4 correspondences. Here's another function, the g function, and we start with some domain A, and we have some select elements in that set, 4, 3, 2, and 1 again. Notice the difference here. In the g function, 4 is paired with 10, just as it was in the f function. 3, however, is paired with 4, and 2 is also paired with 4. I thought that was not a function. I thought that was what we were trying to avoid. Is that still a function? Is G still a function? Now think about the examples that I gave on non-functions. You don't want to run a product through the universal product code scanner and it comes up with 2 different prices, right? Here we've got this item and it comes up with 2 different prices. But is it okay for 2 different items to have the same price? That's okay. That happens, in fact, doesn't it? So is that what we're dealing with here in G, right? We've got 2 different x values that have the same y value. That's legal, still a function. It is true in G that the G of 3 is 4, and the G of 2 is also 4. Now, when we're doing a check in this type of a representation of a function, we would ask ourselves this question. The G of 3 is 4. Is the x value 3 paired with anything else other than 4 in this pairing or mapping? It's not. It's a function as far as that goes. The G of 2 is 4. The x value 2 is paired with the y value 4. Is the x value 2 ever paired with anything else other than 4? It's not. So it's okay. Now if we were to plot points, what is true about the G function that is not true about the F function? What does this create right here, visually, if we were to plot points? 2 points in the same horizontal line, right? That's legal on a function, but that's going to create a problem when we start interchanging the roles of x and y, because those repetition of y values become what when we switch them? Becomes repetition of x values, and we don't want that to happen. So not a problem. These are both functions. It appears that f is a one-to-one function for every element in the domain, set A. There is a single element in the range paired with it, right? And that is not the case with G. G is not one-to-one. And it's not one-to-one because of what is written right above it. The G of 3 is very different from the G of 3 is exactly the same as the G of 2. So those 2 points, if we graphed them, would be in the same horizontal line. Okay, so here's another little schematic that we're headed toward, is that not only do we want to be able to go in the G direction, here's the G direction, we want to be able to start with this set and come back the other direction. Now that's a notational thing. It has nothing to do with exponents. It doesn't mean 1 over G. It means G inverse. So we want to take the domain and range in G and completely switch them around. So what was the range is now the domain, and vice versa. So this becomes a problem because the single element in the other direction is not a problem here. For G inverse, 10 will be paired with 4. 2 will be paired with 1. But this is a problem. 4 in G inverse, 4 is paired with 3, and 4 is also paired with 2. That creates a problem. So you can see the benefit of having a one-to-one function. Every x is paired with a unique y. Flip them around, every y is paired with a unique x. Okay, we could have a table of values. This is a picture, kind of a mapping type picture. Here's a table of values. These are also in your text. This shows you the necessity of maybe flipping the roles here so we can look at similar sets of points, but what we want in return, the questions that we're asking and the answers to those questions are completely different. Here we have n as a function of time, so we plug in a certain time into this function and it kicks out what? Population at that time. Nice convenient little function. So at time 0, we've got a population. At time 4, we've got a population, and so on. We plug in 5, and it kicks out the population. Suppose that we want to interchange the roles here, and we don't want to know the population at a certain time. We want to know what is the time that it's going to take us to generate a certain population. So you see the difference? Instead of plugging in t to get population, we're plugging in a population to see what time it would take to generate that population. So here, t is the inverse function. So if this is the function, plug in t and get in. Here we're going to plug in and get t. So it's exactly the role reversal, the inverse relationship. Now look at the pairing of points. Aren't they the same? Exactly the same? I mean, they're completely interchanged, right? The domain for one is the range for the other, and vice versa. So here's our t values, our initial set that we plug in and generate the f of t. Here's our populations that we plug in and it generates the time. So you can see the difference, the similarities as well as the differences of a function and its inverse. So it kind of depends on what we know and what we want to know. Okay, here are some things that are in your book. I'm hoping this is review. Tell me if it's not. Here's some definitions. We've talked about a one-to-one function. This is what your authors refer to as a one-to-one function. It's called one-to-one if it never takes on the same value twice, or more than once, I think would be more appropriate here. And takes on the function taking on the same value means the same y value, right? Never get the same y value more than once. Now we know, by the way, a function, so it's already got to be a function, so it never takes on the same x value twice. That's understood by the fact that we've said it's a function. And now if we never repeat the same y value, that's in addition to the fact that it's already a function. There's a vertical line test for a function. Is there a corresponding test for a one-to-one function? There it is, horizontal line test, right? A function is one-to-one if and only if no horizontal line intersects its graph more than once. So we've seen why that creates a problem. If we switch the roles of x and y, then we have something that, even though its original pairing was a function, when you flip-flop the x's and the y's, it will not be a function. And we want things to be functions. Okay, this definition 2 on this sheet says let f be a one-to-one function with domain A and range B. So much like the picture that I had up here earlier, then its inverse function, get used to that. Are you used to that notation, by the way? F with a little superscripted -1. Don't ever think that means 1 over f, because it doesn't. It's unfortunate that there's a little overlap with that notation, but it does not mean that. It's not an exponent. It's a notation for inverse. The f inverse of y equals x. Now this little double arrow, what's that mean? Goes both ways. That's true. Let's elaborate on that a little bit. Have you heard of a biconditional or an if and only if statement? So if you see an arrow going one direction, that means that the first piece is the hypothesis, the if statement, and the second piece is the conclusion, the then statement. But if the arrow goes in both directions, what's that mean? You see this, some statement here, and you see an arrow that goes here. That means that the rectangle is the if statement, the hypothesis. I see some of you starting to get that look like, oh no, high school geometry. which was my favorite subject to teach in high school. This is the if statement, this is the then statement, this is the hypothesis, this is the conclusion. That's if the arrow goes one direction. Well, you tell me, what if it goes both directions?
It's interchangeable.
It's interchangeable. The hypothesis could be the conclusion, or the conclusion could be the hypothesis. So when you see that arrow go in both directions, this is true if and only if this is true. First piece is true if and only if the second, and the second piece is true if and only if the first is true. So one automatically leads to the other. Sometimes called a biconditional or an if and only if. This is sometimes abbreviated. You ever see this? IFF, it's not like they misspelled if. I mean, that'd be a tough one to spell, wouldn't it? But it means if and only if. So if part one, then part two, or if part two, then part one. It goes both directions. Now, do you see the relationship there? I think it's pretty clear between a function and its inverse. What are the domain elements in the second part? Aren't they the x's, right? What are the elements in the range? Okay. What are the domain elements over here? The y's. And what are the range elements? The x's. But they're tied by this same thing, f. Only one of them's f in its original form, the other one is f in its inverse form. What's the inverse of taking a square root? Squaring, right? Now, if you take something, I've got a purpose in this. If you take something, unlike most of the stuff we do in here, which I don't have a purpose, if you take something and square it, take the result and take the square root, aren't you right back where you started? If you square it and then take the square root, would you say those are inverse operations?
Not if it's negative.
Okay. But basically, in terms of what happens to that number, what you start with, that's an interesting point there. We'll have to deal with that, by the way. Kind of making sure that the pairing of domain and range elements are the same, so we will deal with that. Probably a better example, maybe I should have chosen this, if you double something and then take half of it, that'll avoid that issue. But that will be addressed. Then we're right back where we started. So you know what composition of functions are. I think we can get to this point today, and maybe that'd be a good stopping point. You know what this is. We've already reviewed that. The f of the g, and the way I said it is in fact what we do. We take the g of x first, do whatever we're supposed to do to take the g of x, take that result, plug it back into the variable position of the f function. So could we do this? That means we take the f of the f inverse Any guesses about what the answer is? We've alluded to it already. Be right back to x, wouldn't it? So let's look at an f function here. Let's say that our f function is 1 and 2. And over here we've got 4 and 7. So what do we know? We know that the f of 1 is 4 and the f of 2 is 7, right? According to that picture? Now let's picture f inverse. Well, if we have the pairing or mapping in f, isn't it already decided what the pairing or mapping is for f inverse, right? We're going to do a little x and y role reversal. In fact, I'll just use the same picture. Except now we start with the range, an element in the range. We come back here. So that's F inverse. So F goes in this direction, and F inverse comes in this direction. Do you see the difference, though? And this is not a great diagram for this. But what was the domain over here is now the range over here, right? It's kind of our target set. It's where we're headed. And what was the range over here is now the domain over here. That's the set we start with. So what do we have over here? We have the F inverse of 4 is 1, and the F inverse of 7 is 2. Now, does that satisfy everything we've talked about thus far? For a function, type, pairing, or mapping, and what its inverse is supposed to be. Now, we don't have a great wealth of values to choose from here. Let me slide this up. Let's find out what is the F of the F inverse of 4. Well, that would be the F of the F inverse of 4. Only got 2 choices, by the way, right? We only have the F inverse of 4 and of 7. So what's the F inverse of 4?
1.
1, right? Right there? And what's the F of 1? 4. Aren't we right back where we started? Right? 4 led us to 1, and then if we look at the other set, 1 leads us back to 4. Well, that's not a surprise, because what did we do? We just flip-flopped them. So if 1 leads us to 4 in one, 4 better lead us to 1 in the other. That's how they were designed. What else do we have? 7 here? What's the F inverse of 7? 2. And what's the F of 2?
7.
7. No big mystery there. 1 sends us to, 7 sends us to 2 in one set, and in the other set, 2 sends us back to 7. So back up to this statement right here. Not that we just proved that, we at least made it believable. What's the F of the F inverse of X? It ought to be X, right? Isn't that what happened in that little pairing and role reversal? So not only is the F of the F inverse of X equal to X, the F inverse of the F of X is also X for the very same reason. Now we'll do more with this. We'll do a little bit more kind of valid proving as opposed to just believability. If it passes both of these tests, then they are inverses of one another. If the F of the F inverse of X is X and the F inverse of the F of X is X, that can only be true if they're inverses of one another. Okay, I think I gave you some problems from 1.5 the other day. You'll check what I gave you real quickly. And let me make sure that I gave you all the problems that I want to give you. And if you can have that prepared for next class, we will be in business. From page 63, 5, does this sound right? 5, 7, 8, 11, 13, 15. Now, did I stop there?
Yeah.
Okay, let's add in 2 more problems. 23. I think these are two problems. One is a word problem that's a growth problem, and the other is a word problem that's a decay problem. And I will see you in here tomorrow. We don't usually come in here on Tuesdays, but we'll be in here tomorrow.